Hello everyone, welcome back. Dr. Kimia is here with another great topic in embedded system. Well, today I'm going to focus on teaching about interrupt and timer, and of course, interrupts are concept primarily associated with hardware and embedded systems rather than general purpose programming. So timers are another essential component of embedded system. Pay attention, stay with me because I'm pretty sure this lecture is going to be really beneficial for everybody out there interested in embedded system, more specifically in automotive application. So whenever we face a time-based problem in an embedded system, we need a reliable way to measure and manage time, right? So now in this lecture, I'm gonna just go over the fundamentals of interrupts and timers and embedded system, including how they are defined and how they are implemented. Stay with me and we are going to discuss this together. Here we are, and I'm going to start this discussion with a simple example, which I believe it will make more sense to everybody because I am pretty sure everybody at some point just had maybe some experience waiting for a delivery guy to deliver something at home to you, right? So I'm going to use two conditions in here. One condition is going to be having a doorbell. Another condition is going to be no doorbell. Suppose that in one condition, I'm going to discuss about what will happen if you're staying at home doing something, maybe even studying, and then you do have a doorbell while you are waiting for the delivery guy. And then I'm going to discuss the second condition, what will happen if you do not have a doorbell. So let's start with the first one. If you have an exam and you're staying at home and you do have a doorbell, what will happen? So I'm going to give you another maybe assumption in here. Suppose that you are waiting for Samsung and they already have a time frame, and maybe that time frame is they told you that they are going to show up maybe sometime between 9 a.m. to 6 p.m. This is the time frame. But if no one is in there at home, I mean, they will not drop the item, right? Consider it's like this. If no one is there, they won't drop the item because if it is Samsung, probably they are going to maybe deliver to you an expensive cell phone. Therefore, they are not just dropping it in front of the door if nobody is there to collect their signature. So I think somehow everybody has such an experience that usually when you have an expensive item to be delivered, usually they are looking for some signature to make sure that you will get your item. Now, we are going to consider two situations. As I said, initially I'm gonna consider that if you have an exam the day after and you are busy studying from home while waiting for the delivery and you have a doorbell. In this case, I would say you are doing a different task, which is studying. Suppose right in here, you are sitting at home and you are studying. What will happen? And that different task is super important. So at the same time that you are studying, you are waiting for the delivery guy as well. So you are doing two different things. And you have also a doorbell. In this case, you are doing a different task, which is studying at the same time. And of course, as soon as the doorbell rings, you can go and receive the package as well. So you are doing both. So the doorbell is interrupting you for some time. And you can receive the package, of course, on time, which is the even. So what I'm going to focus on is you are studying and then you have an interrupt. This is your interrupt. Your interrupt is going to be your doorbell, right? As I mentioned it right in here. So you keep studying, you keep doing your main task, reading and studying, and then somebody will just interrupt you using the doorbell ring. Therefore, I'm going to consider this guy to become your interrupt. Well, what will happen at this point? Now, the doorbell is interrupting for some time, and you go receive the package, and receiving the package, which is going to be, for example, at this part, your event. So delivery is there, you receive the interrupt. Based on that interrupt, you act, you go to the door, you meet the delivery guy, and you receive your package. That receiving is going to be your event. So interrupt is going to be the doorbell. Your receiving is going to be the event. So far, so good. So the interrupting is happening only for some time. You get the package and you can go back to your room and finish studying as well. I mean, you didn't lose anything. You had some event happening. Now you are going back, you continue studying, and of course, you can finish your studying after taking care of the interrupt that was the delivery. Now delivery is done and everything happened exactly based on your schedule. Now let's look at the second case or second scenario. What if you do not have a doorbell? Suppose in here, you're going to study in the book. This is your front door. No bell, no doorbell. In this case, if you do not have a doorbell and you may of course, have the concern of missing the delivery. What is usually maybe the idea that may come to your mind? You're studying, but you need to stop reading and check the door continuously to avoid missing the delivery. Therefore, you do not have any interrupt to only check the door on time, and that's when the delivery guy is in there, right? Therefore, you just keep pause or stop, go check, stop, check, because you never know when the delivery guy is there and you do not want to miss it. You continuously stop and check, stop and check. But what if exactly when you are just coming back to your seat in that maybe short period of the time, delivery is there? And again, you may miss it. If you miss, then you are going to actually be at risk. So this is not easy to deal with if you do not have an interrupt while you are waiting for any event. It's the same for programming. Therefore, you cannot concentrate on your studying, and also no matter how many times you check the door, still you may miss it. There is a chance to miss it. So now you notice the importance of interrupt for programming. Therefore, if we have interrupt, we can continue doing what we do. As you can see right in here, we focus on studying. We do not interrupt ourselves until the actual interrupt is happening, which is the doorbell. So we may pause because of that interrupt for some time, which usually is a short time, to go see what the interrupt is. In this even interrupt is the delivery guy. Then we successfully have the event to happen based on our plan. We receive the delivery and then we come back, we continue studying, and of course we can finish even studying at the same time. Therefore, everything is safe, delivery is done, and we had enough focus on studying as well. But in case we do not have that delivery, that ring or that doorbell right in here, we cannot focus on studying. So we mess up with the studying for the exam the day after, which we have it the day after probably. That one is one failure. No matter how many times you leave your room and you check the door, you leave and check, still this potential is always there to miss it. Therefore, You had no interrupt. You continuously stop reading time to time, which is maybe really overwhelming. And of course, you may miss both option. That's option one. First option is going to be you miss a good studying or preparation for your exam. And of course, you may miss also the delivery. So see how important is having an interrupt in. We are now focused on C programming, how important is to become familiar with what interrupt is and how we can use it in C program. Now, in many of the embedded systems, we have the same story to continuously check the switches or sensors or communication ports of any device or any other input or output, which is kind of impossible to continuously check them and make sure about their functionality, sometimes even about their presence. So if you have so many safety switches or other components in your system, this is not an efficient method to consume a lot of energy and time to keep checking them to avoid any sort of issue which might be considered as canceling your event. In this picture, as you can see, if it is a robot or if it is your real automotive, maybe even cause some even safety concern around, right? So for example, if a robot around a conveyor is moving to maybe pick up some component or dropping some object from one point to another point, and it can sense a barrier as a safety issue, it will stop moving task and will shut down immediately because of that safety issue. So this is happening using only interrupt in programming. As an engineer, you can just have an interrupt in your code, and as soon as, for example, this is maybe a safety detection location, as soon as this robot is maybe moving in this direction or that direction or any other direction, and then this guy is supposed to just pick up or drop this safety, let's say, detection location of the robot can detect something, it can stop moving, right? It can stop moving and not to damage any other object or not to hurt any other human which is around. So see how important is having interrupt. So now it means whenever any safety concern is detected, the task or commands can be prioritize using an interrupt. Or another example can be the actual automotive. This is just another automotive picture that you can see in here with so many different sensors and components that can be input, output. It could be like safety, it could be just maybe luxury feature. Anyway, all of them really important. So let's look at some of them. For example, in automotive, you push the brake, right? Then the brake pedal in your vehicle, then brake is going to be an important interrupt for the vehicle, right? For the ECU. Therefore, as soon as you press the brake, right? Or you press the gas, either of them will generate new signal while you are just driving your feet are on the gas pedal. As soon as you press the brake, that press on the brake is considered as an interrupt to not to just continue the same speed, to stop driving. Or if it is like full, maybe press on the brake to completely stop the vehicle, right? Sometimes you bring the speed down, sometimes you completely want to stop it. It depends, right? So an interrupt is a signal to the processor, which can be sent by hardware or software indicating a new event is coming and how important that event is going to be. So in fact, I would say interrupt is going to be something like an immediate event. And then you are going to look at the processor, not your computer. computer is looking at the processor and it's understanding as immediate event is happening, let's just take care of it. So it is taking the immediate attention of the processor to stop or pause the previous event because the new one is coming. Hopefully now everybody has that clear understanding of why we need interrupt and how important it could be in automated system, electrical engineering, automotive application, automation application, robot control, any automated and automation design. So let's look at microcontroller. What you can see right in here is the structure of the microcontroller, a little bit of the microcontroller, what's happening inside it, and how microcontroller can check the status of several devices using either interrupt or pull-in. Now, if the microcontroller keeps continuous monitoring, that is known as pull-in. So the microcontroller keeps checking the status of the other devices. In here, I'm just explaining it to you. So it's happening through either pull-in or interrupt. So let's see what's the difference. Microcontroller in the pull-in situation keeps checking the status of every other devices, and while doing so it doesn't do any other operation and consumes all its processing time for just monitoring, which causes I would say issues. Therefore pooling cannot assign any priority when doing a task. So how we can solve this situation? If we have a pooling system, right, and this pooling system is just maybe a continuous check-in for the system, but still it cannot generate any immediate action if needed. Therefore, we are just wasting time, wasting energy in there. How do we solve it? In order to solve such a situation, that's when we are going to use interrupt method. And that's why in here, I have it a little bit more complete. We probably go through some loop if we are going to look at a continuous event, and suppose that there is a button right in here as a maybe emergency button or something, which is coming as a signal, as an interrupt in case something is happening. And as soon as this signal is coming inside, therefore the loop start working, because now the priority is going to be this interrupt. So the controller is not expected to regularly monitor the status of maybe this loop or any other, I would say, process which is going on until an interrupt signal is coming. Then it will stop whatever it is doing and it will serve the device that sends that interrupt signal. In this case, for example, this push button is going to be that device. And this push button or emergency button is going to be considered as the priority for the microcontroller. So the controller completes the execution of the current instruction and it will start execution of an interrupt service, which we call it ISR, interrupt service routine, ISR. And now, if you look at the process, if the ISR is being taken care of, again, it can go back to the actual looping and continue the same event. So now you have that good understanding of what's the difference between interrupt and pooling service. If we have only a pooling service, this pooling service will only check, but checking alone doesn't generate any interrupt. It just check. Even if the interrupt is there, it won't stop it, it won't fix it to continue. It will just check and it will just waste time. The way that you were just checking in here, continuously check, 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 check. And maybe that issue is happening like during this, maybe coming back from the home to you, from the door to your seat. That's why it's happening the same. That's going to be considered pulling. We do not need the pulling. We need just interrupt. That's the difference between these two. Now, let's look at the source of an interrupt. which can be either an internal source, especially in automotive application or automation application. The source of the interrupt, it could be either external source, as you can see right in here, or internal source. Now, external interrupt can be sent through the processor from external hardware devices such as sensors or switches. For example, when we press a key on the keyboard or move the mouse, any of them, they trigger the hardware interrupts which cause the processor to read the keys or mouse position. Either it is on the regular keypad of your computer, or if you are using your mouse, simply means you are sending a signal to the processor to take the attention of the processor using that new signal. But how about internal interrupt, which is right in here? About internal interrupt, I would say this is another form which either is software or hardware, even internal. It could be either software or hardware that send an interrupt request signal from a secondary circuit, which is built into the microcontroller. So when a program needs the operating system to read through a source or even a buffer before stopping and becoming available for other tasks, that would be an instance of an interrupt. I would say internal interrupt. So let's summarize what I just explained to you. So we learned that interrupt can increase the efficiency of the CPU by providing multi-process, I would say multitasking, since it is a signal that triggers the operating system to stop working on one process and start working on another process when needed. Also, it will decrease the waiting time of the CPU since external devices are somewhat slower than the CPU. Like for example, if you have maybe a mouse or you have this pen, sometimes they are slower than the internal. These are external and they are slower than the internal. Therefore, if there is no interrupt, CPU would waste a lot of time waiting for external devices to match its speed with that of the CPU. This decreases the efficiency of the CPU, and you need to have interrupt to eliminate this limitation. We had exact same experience during the lab time. Remember, I got you to just use keypad in order to become your external interrupt for your LEDs. Your LED is still your 10 segment LED in the setup in the lab still was your hardware as an output, and your interrupt in the very last part of the lab to just send some signal to the LED, it was your keypad, right? So you need to have interrupt. Now, let me quickly explain a little bit about this picture. What you see in here as ISCR, you may be curious, what is this ISCR? This is interrupt service routine. I'm going to write it down for you, maybe with a different color right in here. This is interrupt routine. I would say it's better to even just call it just ISR than having interrupt service routine is a little longer. So ISR is easier, but you may want to just at least know what is this. So it's interrupt service routine. This is one of them. And then you can see the ISC, which is again interrupt service thread. And then I'll explain what is the difference. This is interrupt service, and this is going to be thread. So now what is this and what is ISR? These two are interrupt mechanism. Both of them are interrupt, but with two different mechanisms. Usually we use them to handle interrupts in Windows that are also, I would say, to refer to a bottom half or maybe top half interrupt handlers. So interrupts are signals that temporarily suspend the normal execution of a program or event to allow the processor to handle a specific event or condition which might be urgent in that situation. When an interrupt occurs, the processor transfers control to either ISR that you can see right in here, which performs the necessary task associated with the interrupt. Once the ISR completes its execution, and then the processor resumes the normal program flow as it was. Then what is right now ISR? Therefore, ISR are crucial for handling time-sensitive tasks. And of course, to manage hardware events. And of course, to respond to asynchronous events in a system, because there are situations that we do have multiple events going on for the same system. Therefore, we have to prioritize which one is first, which one is second, or so on. They play a vital role in multitasking operating system. I would say most of the time those operating system are real-time system, and of course embedded system, which are, I would say, the best, or I would say the efficient handling of interrupt is essential for overall system performance. Now, in majority of cases, a Windows CE driver will never have a real ISR and will instead only have ISCR, interrupt service thread. There are, of course, exceptions to this, such as interrupts that must be shared along with interrupts, means two interrupts are coming together, that have a more time critical approach. So interrupt service thread, in this case, I would say is basically a thread that has an infinite loop around a call to wait for single object that uses a special Windows event. So it's going to be somehow a loop, an infinite loop around a call. So the call is like actually to wait for single object, and it will unblock when the system that is the initial event of the system is against returning from the interrupt handler. So interrupt service routine is commonly referred to an, I would say, a service routine which is dealing with Windows CE. This is created and loaded by the driver to do some early processing on behalf of the driver. Instead of each time you go and handle it, it's already there. You have to just include it in your programming in the best way, in a more efficient way, and just benefit from it. So now, I wanted to see how the microcontroller is going to handle the interrupt step by step. So using that, you can understand this from the doorbell example. Remember, I initially started with the doorbell example. I'm going to go focus back on the same example. And now I'm going to just translate it to microcontroller understanding. Suppose that we are looking again at the case that we have the doorbell. Remember I told you in the first event, when you are reading a book, this is your major job. Reading a book is your major event. And you continue reading the book until actually the interrupt is coming. So how about microcontroller? For microcontroller is the same. The major task, this is the like your experience, this is your experience. This is microcontroller experience. We are comparing them. How about microcontroller? Your major job in here is reading. Microcontroller is just running the main program. This is the major job for the microcontroller. Now, when the delivery person rings the bell, remember that was your interrupt. If this guy is just maybe delivery is coming, that's considered interrupt for you. How about microcontroller? Interrupt for microcontroller could be a signal. So an interrupt signal lets the microcontroller know about the event. So maybe a reset button or anything for the microcontroller could be considered an interrupt. It's the same. Now, how about you heard that ring or that, let's say, doorbell? As soon as you heard that, you stop reading. When you stop reading, it means you receive the interrupt. Right in here, you receive the interrupt and you are going to do something else, which is taking care of that interrupt. Means you go to the door to see the delivery guy. What microcontroller is doing when they see an interrupt. So microcontroller, as soon as they receive an interrupt, they suspend the main program, which was this one. They just write in here, pause, suspend it. Now, for your experience, you just paused and you went to take care of that intro, which was the delivery guy. So in order to make sure you're not gonna miss from what point or at what point you stopped reading, you may go ahead, bookmark, or maybe highlight, or maybe somehow leave yourself something in order to see in what line you stopped reading. So then, how about microcontroller? Why you do so? Because you wanted to just continue from where you left. Microcontroller does the same thing. Microcontroller is going to save the current program state or whatever the register you are working into the memory, right? For a later use. So you just bookmark your current page for later use or to come back and continue and complete. Microcontroller does the same. It will save it. Now, when you get the delivery right in here, what do? That means now you have your attention on the interrupt, means your attention is on your interrupt, which is the delivery guy, to fix that issue. And then you will go back at some point to your major job that was reading. How about microcontroller? Microcontroller does the same. As soon as it just received the interrupt and it is just focusing on solving that problem, it will execute the interrupt routine first, like in here, and then in the next step, in here, when you go back to your bookmark page or whatever that you just stopped at, you will go back to where you left your main job, which was reading in this step. Microcontroller does the same thing. Microcontroller also restores the save program and it will continue from there. Very last step is going to be for you. When you resume reading from where you left, it simply means the interrupt is just now done, is fixed. You took care of that delivery guy, you received your item. So now your focus is back to main job, which was reading. Same in here. Microcontroller will resume program execution as soon as like the interrupt is gone. This is how the process is gonna happen. Now, look at the CPU register in here. I'm gonna just show you the CPU register quickly right in this slide. And as we discussed in internal organization in also lecture one, if you forgot about it, you may go back and look at that. There are two type of construction for the CPU. Remember in there I talked about Newman and hardware structure study and hardware structure, which are the main two structure in order to build CPU, right? So which one was the best? If you can recall, hardware structure is more than 90% of the processors out there, right? Like human and hardware structure. They are more than 90% of the processors, but which one are more important? Newman. Remember, Newman. Newman is more efficient, and the application of Newman structure is way more than the hardware structure. So let me go back to that Newman structure. Remember, in there I said usually we do have it like a closed loop. Many options are there. If one thing is stopped, still rest of the component and event can happen regularly with no interruption. Now, there are two accumulators in our microcontroller. You can see them right in here. Accumulators are A and B. And one combined accumulator, this is one accumulator, this is another accumulator. These two are accumulator. I'm gonna just zoom a little bit to make sure you can see. And I have one combined accumulator right in here called D. What is accumulator? Let me summarize it for you. Accumulator is a register to store arithmetic logic unit results. So my Newman in here, this is a Newman structure. The CPU has registration, which is going to be A and B. And of course, for our microcontroller is 8-bit accumulator, 8-bit A and B accumulator. And when I have D is because it's a combination of two 8-bit, it's going to be a 16-bit, or I would say we call it double accumulator. Now, right after that, this darker green right in here, you can see them. These are index. I have two index register to index to a specific part of the memory location. So these are more focused on the memory location. I would say an index register in a computer's CPU is a processor register or assigned memory location used for modifying operand addresses during the run of the program. This is happening during the run time. That's why in here I can see index register X and index register Y. And right after that, we have a stack point. We call them usually SP. SP stands for stack point. What is that? SP or a stack point register is a small register to specify the, right now, these are the memory location, but in here, these are the location of the last item put onto the stack because like events are going to a stack. This is the last position of the stack. So when you put something onto the stack, push onto the stack or put onto the stack, the SP is decremented before the item is placed on the stack. So I would say the very last one, which is super also important in here, is going to be just looking at the interrupt processing sequence. I'm having like a sequence for the interrupt right in here. This is a sequence. You can see it. So this part is going to be the PC. PC is just a program counter which holds the memory location of the next instruction. Still, this is about the memory location, but this is the memory location of the next instruction. But what I'm showing in here about the interrupt processing sequence, this one is changing from 0 to 1. For example, either of them could change, but let me just look at Z. Or maybe let me look at the I interrupt mask. I already introduced mask, and I'm pretty sure everybody in the class right now is familiar with the mask. So suppose that you do have like a flag or a condition code register. Condition code register, kids, condition code register, we call them flag or we call them even CCR. I'm going to leave it for you in here. CCR. This is the same as what I explained before. I'm going to even write it in here as also flag. Flag or CCR. And this is an 8-bit register that contain individual bits that are set or cleared depending on the result of an operation. So as you see here, if the bit I'm going to focus, let me clean it up. I'm going to focus on one bit to show you how this guy is working. Let me focus on bit I right in here. So if I go ahead and if the bit I is changing from 0 to 1, that means there is an interrupt. Suppose this is changing from 0 to 1, simply means an interrupt. If you trace the line, you can see this is the interrupt mask. Means an interrupt is happening. So the processor is checking all of this register in every sequence to see in which register an interrupt is happening. If it is changing from 0 to 1, means there is one interrupt. Then the processor will stop to offer the service, and then it will look at that interrupt, it will take care of the interrupt, and then it will move to the next step. So if I'm going to summarize this for you, the interrupt processing, I'm going to just summarize it maybe inside this document for you. I'm going to write down all the steps to make sure everyone can understand how is the interrupt process. So I would say step one is first device generate an interrupt. So let me just in here mention it for you. This is the interrupt process. Either in your regular life like that delivery or for the computer, this is the process that the computer or yourself are going through. Interrupt process. Maybe take a note, this is important. There is a step one, which is going to be always your device issues an interrupt to CPU or whatever. So first device or first event is happening. First device is going to send interrupt to the CPU. Send interrupt to the CPU. This is going to be first step. Then what will happen? A step two, this is a step one. A step two, the CPU finish the execution of any current. So CPU finish, or I would say pause, finish or pause the execution of the current instruction. Whatever the current event it is. How about the step three? Step three is CPU test for pending interrupt request. Then CPU tests for pending request. It will figure out which request is now waiting for me. If there is one, it sends a response to the device which removes its signal, its interrupt signal. Then CPU, right after that in a step four, CPU save program. Save whatever program, whatever code, whatever event is happening, it will save the program onto a control stack. I'm gonna just move it a little bit to be able to write to a control stack. And then in a step five, CPU loads the location of the interrupt. Right in here, I'm talking about this one. Now it's about to look at the stack is being right in here, saved. Now we are looking at the location of the interrupt. Location of interrupt. Remember I said this is going to be the location. So next step, step five is going to be CPU. Why did I mention, why did I set CUP? Sorry, I have a typo in all of this. These are all CPU, not CUP. I'm gonna fix all of them. So this is CPU, this is CPU, this is CPU, and then CPU in here is going to be looking at the location right now in the system. So CPU is going to load the location. Location of what? location of the interrupt. Where? Into the PC register. So now, next step, save the content of the register. Now, location is being considered. Step 6. What will happen in here? It will save the content of the register. Then I would say against the CPU, but just save the content of the register. That's the next step. From where? From this control. From control stack. From control stack. Now, next, step 7, what will happen inside the computer or inside the CPU? It will find out the cause of the interrupt. Find out the reason for the interrupt, right? Or I would say even interrupt type, or what is the interrupt type, and accordingly it will take care of it. And the very last step is going to be step 8. Is going to be now restore saved register from the stack. Now it will go back to the major job or major procedure, and it will continue from there. So that's why I say it will restore the save registers. And it will continue from there. And finally, everything which is restored, it will restore to dispatch. It will just go back to the original process. So restore the save register. I'm going to add one more. I said it verbally, but even in here, go back to the original process. Go back to the maybe major task or original process. So these are actually, I'm going to just minimize it in case you wanted to take a screenshot from my return interrupt process. This is going to be the interrupt process. You may want to take a screenshot for your review, and I'm going to bring this down. And then one more time, we've got two types of interrupt. Interrupt could be maskable and non-maskable. That I explained maskable and non-maskable during the lab time. I'm gonna also just quickly explain them right in here for you as well. So microprocessor has a vector table that contain just vectors. In embedded programming, vector means memory address, not a dimension or direction. I'm going to write it in here. Vector means memory address, not dimension, not direction. So a vector table, which you can see right in here, contains memory addresses of interrupt, I would say exception handler, routine, and so on. So of course you can say it define where the code of a certain interrupt or exception routine is located in the microcontroller. Somehow it's just giving you the address where you should go in order to find out what's going on. So when an interrupt is happening, the program moves to the interrupt handling routine, which has some information like in this one, and the address of the handler is provided in interrupt vector table, or I'm going to even call it IVT. IVT stands for interrupt vector table. So interrupt is let's say if interrupt is a reset, what will happen? If interrupt is a reset, simply first priority for the microprocessor is going to be stop or pause the executing of the main program as soon as you can. And of course, go take care of that reset and see what's happening in there. Now, let's look at here. Reset, I said it before during the lab time, either the hardware or the software. Reset is always the main priority for the microcontroller. That's why in here I said this is like This is like non-maskable. Non-maskable, these are priority. Clock monitor, again, is the type of reset. COP failure is a type of reset. Unimplemented instruction trap, anything like that, these are non-maskable. These are non-maskable. Now, we cannot have, for example, non-maskable and maskable at the same time for a, so like for example in here, for a command or for a signal. This one is non-maskable interrupt, XIRQ. If there is X, this means this is non-maskable. And if it is IRQ alone, this is maskable interrupt. So we cannot have a switch between these two. Such as, for example, if we have like keypad and we practice already the keypad. We cannot just have it to switch between, like switch to be a non-maskable interrupt. So when we press a key inside the keypad and you did it using the laptop, microprocessor will check only that certain key. It won't check at the same time, few of them at the same time, maybe uh, A and B or 2 and 3 or just that certain key. So that's an interrupt. It's just checking 1 if you press 1. If it's just checking 0 if you press 0 or A or whatever. So that's why we say only that key, not all other keys, is going to be the interrupt. So you can see I already just labeled them. These are going to be the lower priority. These are the highest priority. If any of this information right in here is happening for the microcontroller, of course, microcontroller will give the priority to either of this interrupt rather than taking care of the lowest priority. Lowest priority, for example, pulse accumulator A overflow or something like that. These are lower priority. Now, I already introduced the interrupt type. As I mentioned, we have two types of interrupt, maskable and non-maskable. I'm going to look at the maskable and non-maskable quickly in more detail. Earlier in the lab time, a mask is just really clear for you right now. It's defined, means we are going to bitwise something. Some of the bits are going to be as it is. Some of the bits are going to change. So now a mask defines which bits you want to keep and which bits you want to clear. Right? Masking is the act of applying a mask to a certain value. Simply means if you have like maybe 1, you wanted to mask it, probably you wanted to turn it to 0. You are going to apply a mask to it. Masking is the act of applying uh, a mask to a value. Now, the main difference between maskable, remember for maskable, I said you can say IRQ, and non-maskable XIRQ interrupt is that a CPU can either disable or ignore a maskable interrupt, but it is not possible to disable or ignore a non-maskable interrupt. And the CPU must immediately act on that non-maskable interrupt. Now, if I go back to that, like in here, look at here. So for example, also both of these two are considered highest priority. But non-maskable interrupt never could be ignored, but the IRQ or maskable interrupt, sometimes also it is priority, but you can ignore it. For example, the reset interrupt or clock, as I said in here, reset clock, these are both non-maskable. And the microcontroller must immediately execute them. Microcontroller cannot ignore them if either of those signals come in. For example, while you are writing your program in the lab and a maskable interrupt such as either reset or clock, monitor fail reset or something like that is coming, a maskable interrupt is happening. You can reject it or cancel it and continue if it is a maskable interrupt. But you cannot You cannot just continue if it is like a reset, which is non-maskable, right? If it is, for example, a maskable, yes, ignore it, continue. Non-maskable, you cannot ignore it, and you cannot continue. You have to just take care of that. And then so the interrupt priority or IVT table, which I'm going to repeat right in here, for every type of microcontroller it could be different. And if it is maskable, you can change the priority based on your application. If it is non-maskable, you cannot change the priority, and you must go there and you must take care of that priority first. Now, for our microcontroller in the lab, there are 128 interrupt services. I'm going to show you the structure right in here. We've got 128 interrupt. Remember one more time, the microcontroller we are using is HCS12, which is a common microcontroller in automotive industry. And then only 6 of them are non-maskable. Rest could be still maskable. I showed it in the previous IVT right in here. See how many of them? 1, 2, 3, 4, 5. So just 6 of them. Six of them are non-maskable, which I summarized this exact same one right in here for your information. And the rest are maskable. So now, when I say XIO, XIRQ, you see a non-maskable. This is a non-maskable interrupt going to my HCS12 microcontroller. And then right after that, this one you need to pay attention. Any non-maskable going to the microcontroller is not ignorable. You cannot just leave it as it is. But anything in the other side, you can see right in here, IRQ0, IRQ1, IRQ2. These are maskable. These are still interrupt, but these are maskable. This is non-maskable. I show it with anam. These are maskable. I show it with only interrupt. So with M. Now, how to define an interrupt in C? We already practiced it. I'm gonna just quickly review this part with you. Although I know everybody should be at this point really familiar with this procedure. We practice during the lab time quickly. Interrupt vector number right in here. This is going to be like creating other function in C. I already told you, in order to create a function, we have to go through 3 steps. You have to define the function, you have to define the function prototype, you have to define the function call inside the main. So now when you are defining an interrupt in C, you are going to define it, or you are going to create one function, best practice, as I said before, after the main. And then this is the structure, interrupt vector number, and then anything as a routine, any of your service routine is going inside here. So this is just a void function. This is the function body. You have to go ahead, complete the function body based on the structure. And one more time, this is the header file for the microcontroller. You must always come here, look at the information, look at the vector numbers and everything inside the library. Now, I'm going to just solve one example for you right in here. This is an example to practice how to use interrupt. We already did it during the lab time, so I'm going to just repeat one more time. I'm going to have a non-maskable. Why? Because this is XIRQ. And this is a pin that is connected to a switch that is high. So I'm going to have a switch. I'm going to have a pin of that switch to be connected to normally high. And I'm going to send a signal, which is XIRQ, means this is non-maskable. Now, if the switch is low, this is the understanding from this question. If the switch is low, then it should turn the LED on. My LED should go on. Pay attention. And I mean, when it is on, 0 means off, right? 0 means off. When I say turn it on, means the switch supposed to be set to on. or turn on or set it to 1. If I set switch is off or 0, these two are the same meanings. Or you can say high. That's why I said in here like the arrow. This is high and this is low. These are all the same thing. Now, I'm going to turn the switch to become on. Therefore, first thing, I'm going to start inside right in here. I'm going to go ahead first define what is my data direction to port B. This is port B. This is the same port B. I'm going to give them data, give the port B data direction. And that direction is going to be, I'm going to set the PB4 to output. In this line, I'm setting the PB4 means bit 4. Port B, this means, I'm going to translate it. This means port B bit 4 is set to output. This is what this line means. This is the first thing. I defined it. Direction, which is port B, or the like bit 4 is going to be right in here. I use or, and then I say, okay, now this is going to be data direction for port B. I'm going to give it data direction to mask bit 4. Mask bit 4, which is 7 bit 4 to output. I do the same for here. I'm going to say port B. Now port B and what is this? Not mask. Don't mask it now. And not port B bit for mask. This is output in here, but I don't want this to become 0. Excuse me. I want it to be set since PB4 is normally on. I want it to be low. This is normally on. Now I want it PB4 is normally on, means normally 1. Now I want to set it to 0 or low. I'm going to set it to low because in here it says whenever the switch goes low, it should turn on an LED. Right? Now, next, I'm going to look at the interrupt. I go back to the IVT table, right? And from the table, I have to figure out, this is what we figure out from the table. I have to use interrupt. I get this address from the table divided by 2 minus 1. And then I'm having a void function for the interrupt. This is just any name that you can pick. This part of it is a name. This is a void function. And then I'm going to toggle bit 4 right in here. So then I have to say port B bit 4 mask means toggle bit 4. So here we use XOR. This is XOR, kids. I explained it in the previous sessions. So this is XOR. So I'm going to use XOR to toggle bit 4 accordingly. So I would say port B XOR port B mask bit 4. So this one will toggle bit 4. Now, I'm going to finish it up right in here. Why timers are important. Next time, I'm going to continue with a little bit more with the basic of clock. These slides are all from the lab. That's why I'm going to just finish it up with the timer function importance. So far, we finished the interrupt and the timer. I'm going to discuss it with you next time. Take care, stay tuned, and we'll see you again on Thursday.